Hey everyone, it's Mr. Naylor. Good to see ya. Well, all right, I guess I can't really see you, but you know what I mean. I'm glad you're here. I apologize that I am not, but what we're going to make sure is, that's right, we're going to make sure this is still a day of learning. All right, so what we're going to end up going through today is the exact same thing you would have done with me had I been here. So listen, this first piece of today, this warm-up, it's not just kind of filler. It's actually a chance for you guys to try to make an extension with domain and range. Domain and range can be a little tricky in the first place. Now I'm asking you to extend it a little bit. So you got to take the approach that you're trying to figure this out. Okay, you're going to need a calculator. So when you're ready, get a calculator, get out your notes. You're going to want to, get into these two equations. You're going to want to try to find the domain and range for the tangent of 3x plus 90. Notice that I'm trying to get you to do that without a calculator. And then the domain and range of 3 cosine plus 1. And you can use a calculator for that. Okay, now this is the part in this sort of remote video lesson where you need to do this. You need to actually pause the video. Okay, don't just keep watching, because I am going to go over it. But you need to try to get the domain and range. Okay, how are you going to do that? How are you going to do that for this tangent function? Okay, a little bit of a hint. You can't use a calculator, but you still need to think about the graph. Okay, because you need to think about the asymptotes. I wonder if you can get the asymptotes for the tangent of 3x plus 90. That's what you're trying to do. All right, without your calculator. Pause the video, so don't keep watching. That's right, you need to pause the video, all right? Next time I start talking, I'm going to be going over the problem. So if you haven't paused the video yet, pause the video now. All right, so like we said, you're going to need to think about the graph. I'm just trying to get you to think about the graph of tangent of 3x plus 90. Ultimately, so you can think about the asymptotes, because the asymptotes are not in the domain. Okay, that's what we're really trying to determine here. So sketching the tangent of 3x plus 90, remember 90, that's not the shift, but it's related to the shift, right? Okay, you got to use this 3, we call this the k value. We got to take 90 divided by 3. So 90 divided by 3, that's the shift. And of course, when it's a plus sign, it's actually a shift to the left. It's kind of the opposite of what you would think there. Now, since we also have a period that's going to sort of be affected by the asymptotes, why don't we think about the period, which, remember, it's always the original period divided by that k value. So we do have a period of 60 degrees. Now, these two numbers in gold and blue, they're going to help us to get the graph of this function, right? How do they help us to get the graph? Okay, well, we have to think about where the original tangent graph starts, and then, of course, shifting at 30 degrees to the left. Now, we're talking about like the starting point, sort of the original y-intercept is now in that position. Now, the period is always going to be the total distance between the asymptotes of a tangent graph. So what I always like to remind students is what you really want to think about now is half the period. Okay, now that's pretty easy to find. Half the period just ends up being 30 degrees. But that means that you can travel half the period this way and half the period that way. You can travel half the period from the center. And that's going to land you on an asymptote, or it's going to take you back to an asymptote. Okay, yeah, the graph is going to be doing its thing in between here, but the whole point here is that you want to shift 30 degrees, and then you want to use half the period. You want to use half the period to be able to go back and forth to an asymptote, which is going to take you back to 0, or it's going to shoot you all the way over to negative 60. Now here's the thing, the domain is going to not equal these asymptotes, okay? But we need to do a little better job of describing them instead of just saying that it's not going to equal those asymptotes. And this is where that formula comes in. Remember that formula? You should have went back and looked for it. If you didn't go back and look for it, shame on you, okay? Because the formula always uses this sort of this format of all x such that, and then we talk about not equaling those asymptotes. Now listen, the asymptotes are how far apart? That's right, they are 60 degrees apart. Okay, it doesn't matter which ones you're looking at, all the asymptotes are 60 degrees apart. That distance, the distance between the asymptotes is going to end up being the number that you put in front of k when you use this k formula. And then you always want to add your first asymptote. Well, your first asymptote was technically at 0. In other words, if the asymptote is at 0, then we can just call that our first asymptote and don't even need to add that there. Okay, we could kind of just clean this up to just be not equal to 60k. All right, that's the domain when we have a shifted and adjusted period. The range is always negative infinity to positive infinity. Okay, that's kind of a freebie. The range is always negative to positive infinity. And when it comes to a cosine equation, it's the same thing with the domain. It's a freebie. It's always positive to negative infinity because a cosine graph, of course, goes left and right forever. Let's take a look at that cosine graph. You did graph it, right? Did you notice some things that were a little different about this graph? Okay, well, when it comes to the range, all we really need to do is figure out how high and how low the graph goes. Now, you can kind of see that just visually on here. It seems like it goes as high as 4 and as low as negative 2. So pretty much that's your range, okay? Your range is between negative 2 and 4. But there's something else going on in this problem. Did you notice it? Did you notice that the entire graph, that is the middle or the midline of this entire graph, has changed? And that's because we have a new transformation. Now, something that I want you to get from this warm-up is this additional concept that if you add a number to the end of an equation, that's always going to be a vertical shift. It's actually going to be a vertical shift of the midline. We haven't seen this yet, but today's the day where you get to see it. And I think this would be something perfect for us to fill in as a new set of notes. Remember the notes that we took the other day and you guys use these boxes? Well, I'm going to encourage you to make a new box where we can put in this idea of a vertical shift. Okay, use your notes, make another box, go back to the other day, and let's make a statement about how the number at the end of the equation is going to shift the midline. Okay, yeah, it can look like this. Basically, if you have a sine or cosine equation and you add or subtract d at the end, that's going to be the new midline. And as I hope you see from this warm-up, that's also going to affect the range. It's going to affect the range as the midline ends up shifting up. Just going back to this equation, I want you to notice that the amplitude is still measured from the midline. Okay, the amplitude is still the number 3. Remember, that's the number that's in front of the entire equation. But it's kind of cool because if the midline is at 1 and the amplitude is 3, Oh yeah, I would go up to 4 or go back down to -2. We're going to add this concept to our tool belt, the concept of a vertical shift. All right, when you're ready, we're going to move to the homework. Okay, we typically take some opportunity to go over the homework. Now, if I was here, I might have drawn your attention to number 4. I would still like you to draw your attention to number 4. If you got that equation correct, great. I still would like to follow up on it quickly, just not knowing if you got it or not. Remember, number 4, the period was 180 and the shift was 120. There was also an amplitude, but that's pretty easy to get. Now remember, the period is 180, but that means that the original period divided by k is going to equal 180. So if we solve that equation for k, we get k equals 2. And the shift, of course, the shift is 120, but that would equal c over k. Well, we already know that k equals 2, so we can say that that would be c over 2. And if you solve that for c, you get 240. Okay, so we're using those same formulas, but we're kind of solving them for k and for c. How'd you guys do with number 7 and or number 8? I'm sorry, I meant number 6 or number 7. Those problems were in radians. Okay, let's take a quick look at number 6. Now the period was given to us as pi over 2. Being a trigonometry student, you'd want to recognize, oh, okay, that's in radians. So that means we have to kind of adjust our formula to be in radians. What does that mean? Well, it simply means that the original period is no longer going to be 360, but instead we're going to think of 360 in radians. So that's right, it's going to be 2 pi. So it's still the original period over k, this time 2 pi over k. Well, we might need to do a little bit of solving, if you will. We might have to do a little cross-multiplying. Do that. You end up getting pi k equaling 4 pi. So, okay, we can solve that for k equaling 4. The only thing that's different is that we have to adjust our original period, and we have to think of it as to be in radians. Okay, if you have any other questions on that homework, it'd be something that you could reach out to me. We could still go over it the next time we're together. What we're going to do now is we're going to move into the main part of today's lesson, which is to kind of do the last step of graphing, which would be to look at a graph and write an equation. Now, I want you to use the graphing sheet that was handed out to you, hopefully that you got, and we're going to basically treat most of the front of this like notes, and then the back of it becomes a little bit more of your homework. Okay, so we're going to write equations, but now finally from a graph. This is kind of the final step in our little journey here with understanding graphs. A couple things that I want you to realize. Each one of these graphs is in a typical Zoom Trig, sort of Zoom Trig window. So that means that essentially the x-axis goes from -360 to 360, and the y-axis goes from -4 to 4. The other thing that you want to realize about all these graphs is that any type of shift and or period is always going to be a nice angle. That means it's going to always be something of the multiple 30, 60, 90, or 45. Again, any type of shift or period is always going to be a nice multiple. Multiples of 30, which would also be 60 or 90, and or 45s. Okay, now you'll catch on, but each one of these problems is meant for us to kind of notice something new, so don't sort of skip ahead too far. I'm going to do numbers 1, 2, and 3, each one of them, to try to show you something new. Before I forget, everything about today's lesson goes back to the parent graphs, and the parent graphs is what I have on this side of the screen. I mean, you can write them down again if you want, but you should already know the parent graphs and notice where they start. So it's just something that we're going to reference as we go through this lesson. That's why I have them written there for us to look at. All right, so we ready to look at this first graph? I'll tell you what, before we really jump into it, just want to make sure everybody's clear. Because this is in Zoom Trig, each one of these little checkpoints is 90 degrees, the same thing as, we've seen on the calculator. So 90, 180, 270, 360. I'm going to erase those. It gets a little too messy, but that is definitely assumed. Well, if we're going to write an equation for this graph, we pretty much need all the specs. How about starting with the amplitude? It's probably the easiest thing to see. Remember, the amplitude is the distance to a high or low point from the middle. It's basically the distance from the midline. So, not anything too complicated here. You're just kind of looking at the graph and counting, I suppose, a little bit. You should deduce that the amplitude's 3. Pretty much you can just fill that into the equation. I don't need to do any fancy math other than just put it in there. What's next? Well, this is where it gets a little trickier. We definitely are going to need the period. And to be honest, we're also going to need the shift, but one thing at a time, right? So let's start with the period. Now, the period of a sine wave, or for that matter of any graph, is always one complete cycle. In other words, we have to find 2 points that sort of denote one complete cycle. Now, my eyes and a lot of students' eyes will kind of go to these 2 points because, well, we see the full sort of up cycle, and then we get kind of the full down part of the cycle, and you get back to where you started. So point to point would be considered a period. So now the question is, what are those points? Well, listen, this is where you have to remember that I said I'm only going to give you numbers that are in multiples of 30 or 45. So one would have to realize that the first point here, this one kind of on the left, is, it's definitely not a full 90. It's somewhere between 0 and 90. Do you think it's at 60? I don't think so. Would it be at 45? Then it would look like it's right in the middle. Well, since it's not right in the middle at 45, it's got to be a little bit skewed. It's at 30. So that's a 30-degree, starting point. So how about this other one over here? Looks like it's a little bit past 180, doesn't it? Yeah, it's 30 degrees past 180, so it's at 210. Now, you can write that stuff down. You can just kind of get those numbers in your mind. But basically, the difference or distance between those numbers, that's your period. Okay, so the period is 180. Now, most students are going to continue to analyze the graph. That is to realize that we also need to come up with the shift. Now, the shift is always of the original y-intercept. In fact, there's a little song that we sing. It goes like this: oh where did the y-intercept go? Oh, where could it be? Now, don't get me wrong here. I'm talking about this original y-intercept. And what we want to do is we want to notice where it went. Okay, now where it went for the graph that we're talking about is a little bit to the right. It's actually right there, because the graph that we're talking about then goes on its merry way. So sometimes people get confused and they say, Miss Naylor, do you mean the x-intercept? No, I don't. I mean, where did the original y-intercept go? And the answer is it went right there. Or if we go back to the graph that we're studying, it is right here. It is this point. It's 30 degrees to the right. That is the shift, again, of the original y-intercept. Okay, now we want to be careful that we don't maybe say that it's this green point. That's because the graph is going down from that point. Something that's implied here is that a graph, or a sine wave, I should say, is always going to proceed in an upward manner from its original y-intercept. So that's why 30 degrees to the right is our shift. Now, remember, these two specs, they're nice, but what we really need is we need C and K, or the other way around, we need K and C. So we're going to, of course, use the original period divided by K equaling 180 so that we can deduce that K equals 2, and we'll be able to fill that into our equation. And then we're going to use the C over K equaling 30. For this problem, of course, that means that C equals 60. So we're going to fill in 60 right here. It is a shift to the right, so we actually use a minus sign. Be careful about that. And voila, we have 3 sine of 2x minus 60. If I was in class with you, we might graph that on our calculator. You can certainly graph it if you want as a little check. Okay, but what I want to do now is move on to the next graph, which it's a tangent wave, and obviously we have some stuff to talk about here. How about we start by saying that there is no amplitude. Now, there still could be a number that could go in front of tangent, but it wouldn't be considered the amplitude. It would simply be some type of transformation stretch type number. That's not going to happen right now, so don't worry about it. We're going to move on to the period. Now, we've been talking a lot that the period is the distance between the asymptotes. Yes, that is definitely true, but I don't have any I don't really know where the asymptotes are on this graph, at least not right at the moment. And I don't want to talk about imaginary lines when I can actually have actual points. You see, a period is really just what it takes to see one full cycle. Well, from point to point, I get an up and a down part of this tangent wave. In other words, I get one full cycle. So I'm going to suggest that we go point to point for the period. Let's talk about the point. Remember, only multiples of 30, 60, or 45. This is a good example of a 45. Okay, basically, the first point is at 45, and the next one is at 135. Okay, how do I know that? Because I see where they are positioned on the graph. Now remember, the period is still the distance between those numbers, and so we end up with a period of 90. Ready to talk about the shift? Oh yeah, to talk about the shift is to talk about the original y-intercept. Oh, where did the original y-intercept go? Oh, where could it be? Okay, if you think about the original y-intercept of a tangent graph, it starts right there again at 00. But where did it go? That's right, it shifted 45 degrees to the right. It shifted to this point. Wait, what's that you say? It could have also been 45 degrees backwards? Yeah, actually that's also true. Basically what we do is we pick the closest shift point. But in the case of this problem, it's a tie. It's 45 degrees left or right. Now, as long as you said one of these, you would be correct. But just to be honest, that for this problem, we could be giving both. Okay, so it looks like we got a period and we got the shift, so it's time to come up with your equation. Kind of a similar procedure here. You want to solve for K. Yes, 2 is a common K value, but please don't just assume that it's always 2. Problems are going to get a little trickier eventually, but we can also solve for C. C over K, C over 2, so C equals 90. Now, I can put in a 2x plus or minus. Yeah, plus or minus, because it shifted left or right. Now, like I said, as long as you had one of those, you would still be correct. I know, we didn't do anything with the asymptotes. We didn't need to. Okay, are there asymptotes in this problem? Yes, but I didn't need the asymptotes to be able to determine the period, and I certainly don't want to use the asymptotes to come up with the shift, okay, because remember, the shift is, oh, where did the y-intercept, the original y-intercept go? We got one more graph, kind of talk about one more kind of new idea, and then we'll let you guys try to work on the rest. That's what we would have done anyway. Let's talk about the amplitude. Careful, careful, careful. Okay, the amplitude is always measured from the midline. Oh, maybe I better come up with the midline on this problem. Now, just kind of, again, visually, you should be able to see that from the midline, we either go up 1 or down 1. So the amplitude is 1. But again, that's carefully making note of the midline. because amplitude's always measured from the midline. Wait, what's that you say? The midline has itself shifted? You're right. That's exactly right. We actually have a vertical shift. So I was wondering when you would get that. Now remember, we just talked about that in today's warm-ups. We had a vertical shift up 2. Okay, if you're already ready to put that into the equation, you're ready to put a +2 at the end. Pretty cool. The midline was helpful in getting the amplitude, and it was also helpful in getting the vertical shift. By the way, the amplitude's 1. I can put a 1 in front, or of course that's assumed to be there. Period. Point to point. Now what I'm showing here are probably the 2 most common points for kids to notice. Simply being able to get a full period, basically back to where you started. Just saying, it wouldn't have to be those points. If I was in class with you, somebody might have asked or somebody might have suggested, hey, Miss Naylor, you could have gone from these points. Okay, yeah, that's 1 full period. Notice that it kind of shows you like a different starting and ending point, but it doesn't matter. It's still 1 full period. Okay, just keep it simple though. We're going to stick with the original ones I gave. Okay, 0 degrees, yes, is the starting point, and 180. That's pretty straightforward. That means that the period itself is 180. Okay, I didn't have to really do too much thinking there about other angles. Ready to talk about the shift? Yep. One more time. Where did the original y-intercept go? Wait a minute. The original y-intercept, you're talking about that point up there? I am talking about that point right there. Where did it go? Where did it go? I wish I was in class with you right now. I could see the look on your face. Anybody kind of have like a look that it didn't go anywhere? Wait, what do you mean it didn't go anywhere? Well, I mean at this point did not move left or right. It didn't go to the left. It didn't go to the right. It's where it started. Now, if you're saying, Miss Naylor, but it did move. It moved up. We already took care of that. That's the midline. But as far as left and right, the original y-intercept is still where it was. In other words, it's on the y-axis. So there is no horizontal shift. Let's kind of distinguish the shifts here. So horizontal shift, none. Again, that's because that point did not move left or right. It's still in the same place, left or right. All you got to do is find the k value, original period divided by k equals 180. I know, k equals 2 again, even though I just got done telling you that's not always 2, but it was again for this one. Now, this is kind of like a beginner's, if you will, basically assignment, or it's actually a homework assignment for writing equations. Just letting you know, we beef this up as we start getting into the applications of these graphs. We're not there yet. What you want to do right now is just kind of take your time, try to keep these graphs simple. What I mean by that is most of them only had 1 or 2 transformations. Okay, don't get too complicated. Just try to look for 1 or 2 transformations. Now, I do have one problem down here that starts to get you to the next level. Interesting. 1 graph, 2 different equations. 1 graph, 2 different equations. Give it a good shot. We're going to call this homework. Could be checked next time. And I'll be looking forward to, of course, continuing our study on trig graphs and transformations.